As we know, in engineering we don't need to go to the same level of depth as physics. You don't need to know Lenz's law. You don't need to know the right-hand rule, the left-hand rule, which direction a wire moves if it's carrying current in an imposed field. Don't need to know any of that. What you do need to know, if I put current into a motor, that's the symbol for a motor, it spins. Conversely, if I spin a motor, this polarity here is important, it generates an opposite current. So at the same time when you put electricity into a motor, it's generating a current that's opposing the voltage, if that makes sense. Because if not, if you just kept on feeding power into a motor, it's making it spin with a force, and then the longer you leave the motor on, the faster it'd spin until it'd get up to something stupid like 400,000 or 500,000 RPM and it'd self-destruct. Something's got to be stopping the motor from going too fast. That stopping the motor from going too fast is called back EMF. When you put the power on the motor to make it spin, it's also generating a reverse voltage. When it gets to the fastest possible speed it can do, here's RPMs. There's your back EMF. EMF. I don't know the exact shape of that curve. EMF doesn't end in a letter E. EMF. That says EMF. Gets to a point where let's say it's 240 volts. It's generating 240 volts going backwards. Generators always produce an AC signal unless it's rectified. So that motor, I think it's a G for a generator actually. That motor, when I power it up, generates a back voltage. When it hits 240 volts, the motor cannot go any faster. Make sense? Done. Back EMF, motor control. Actually, yeah, just if you don't mind, I'll just continue with it. Sorry, my fault. They're all laughing in the background because I was finished, but it's a perfect lead-in. Is everybody clear on that? Yeah. Okay, so your syllabus, and I'm going to go a bit on personal and public, then I'm going to stop and go to cracking. Your syllabus talks about how to control the speed of a motor. The physicists know one way. What's one way to control the speed of a motor? Voltage. Yeah. Less voltage, less force, doesn't spin so fast. More voltage, the motor makes more force, spins faster. So to control a motor, you can control the voltage. That works for AC and DC. There are other ways, or let's actually look at how to control the voltage. To control AC voltage, alternating current, is a sinusoidal wave produced by the generator. Looks like that. This might be minus 240 volts, that might be plus 240. The voltage out of a generator is a sinusoidal wave. Let me see if I can actually hit the mark properly. There you go, that looks better. How do you control the voltage? You just lower the height of the peaks. DC voltage, that's AC, alternating current, going above zero, that's 0 volts. Negative, positive, negative, positive. DC, here is a battery that is running at 9 volts. That's yours time, that's voltage, that might be 9 volts. This is also DC. because it's always positive, if that makes sense too. You cool with that, everybody?
Yeah.
Anything new in this compared to what you learned? Not really for the physicists? Not really? Okay. So, what we've got, do you agree that that one there is DC?
Yeah.
Here's the other way they control motors. Pulse width modulation. Mean anything?
No.
This is new and it's syllabus content. Watch on. So there's time. Here's 9 volts. If I turn the power on for half the time, turn it off for half the time, in that square wave, the average voltage is now not 9, is it? The average is, if that's 50%, that's 4.5. What happens if now I leave it on 9 volts for 80% of the time, turn it off for 20%, I've just drawn that in there about the scale. What's that now? 9/8?
7.32.
Yep. So that means there. So if I leave it on for 80% of the time, it's 7.2 volts. Pulse width modulation, but it's not once per second. This might be 200 times a second. They flick the voltage on, turn it off, flick it on, turn it off, flick it on, turn it off, flick it on, turn it off. So in that 1/200th of a second, it might be turned on for 80% of that, turned off for 20% of that 200th of a second, then on off, on off, on off, on off, on off, on off, and it just sees the average. Yeah? That's how they control speed of a DC motor, pulse width modulation. Definitely examinable because it has been 3 times, not recently. Hint, hint. I don't know where they're going to go, but pulse width modulation has not been examined. It's in your book. We'll cover it tomorrow. That's one way they control it. The other way, since it's already been covered in physics, variable voltage, variable frequency, triple VF drives. Yes, no? Physicists?
Strength of the magnets.
Yep, that's, but in a motor, the only way you can control strength of a magnet, like you can't go in the middle of the night and change the magnets in a motor to change the speed.
Nah.
Not practically. Okay, the other way it's done, just watch on please. So that's DC, that's pulse width modulation. Okay, the way it's done in AC, every time that AC wave hits the top, it gives the motor a little kick that makes it spin. In AC motors, every time it hits the top of the wave, it gives the motor a little kick, makes it spin. If you want to make it spin faster, wouldn't it make sense to kick it more often? Yeah?
Suppose. Or the strongest.
Say just stronger, but you're already at maximum. You're at 240 volts, you can't go any faster. Okay, going stronger does not make your motor spin faster, it does give it more torque. Okay, doesn't change the speed, does change the amount of power behind it, force times distance, torque. Now, what we need to do, they get this AC wave through electronics, they break it into DC. And then they just add it up with electronics and they just recreate the wave as, let me just draw it in as little steps. The finer the steps, so if that was 240 volts and 50 hertz, I can break it down and I can make it into something that's a lot quicker. If I make it into something that's quicker, it gets more pulses. And you have heard this. Have you heard motors sometimes, they've got a really high pitched hum to them when you change their speed? This one up here, this is your dimmers on your fan switch probably. If it's just a simple resistor, it's just cutting down the voltage. The electronic dimmers do this. In the back behind the knob, there's one of those. The smoother those transitions, the less hum the motor makes. Variable frequency drive. And as well as changing the frequency, they can also change the voltage. Yeah? Just by recreating the signal. So AC motors are controlled with variable voltage, variable frequency, which is triple VF, variable voltage, variable frequency. DC motors are controlled with pulse width modulation, and both motors can be controlled just by dialing down the voltage by putting a resistor in series. Old school trains used to have the train driver there. Here's a train carriage, electric train carriage. There's the pantograph on top. Looks beautiful. I think it's one of the old red rattlers. The train driver sitting in the front just used to have a lever, and he just used to slide it to the left, slide it to the right, and he was just changing the wiper on a variable resistor. On top, those lines on top travel at 1500 volts. The wheels are connected to ground. So, the old school trains, 1500 volts DC, going down to ground. There's a problem we'll cover with DC voltage, that is, it runs out really quickly and you've got to have lots of transformers. Okay, cool. Motor control. The AC motors, if they put that 1500 volts AC, first thing that happens inside the train is there's a box, AC goes in, DC comes out, and then it goes to the motors. And then in here you've got triple VF. The modern trains use AC voltage, convert that AC, which must mean that line is now AC all the way along. The modern trains convert. Yeah? Then drive it. Let me get back to you on that one. I think they might even be DC. For conversion purposes, they turn the DC into AC inside the train, modify the signal, send it out. Let me get that 100% back to you.